Hi everyone. So when you're solving a 4x4 Rubik's Cube, half the time you'll get OLL parity, which sucks because it's a very long algorithm, typically 15 moves or worse, and it's not very intuitive. You could learn OLL parity avoidance, but learning how to trace through 12 edges of the cube in 15 seconds of inspection could be pretty difficult. So let me show you a method for solving the 4x4 where you'll never get OLL parity and you don't have to trace edges around the whole cube. I'm calling it Weird Lewis because it's the same as the Lewis method for solving the 4x4, just that the steps after CMLL are different. Let's do an example solve. Here's the scramble if you want to follow along. Now, the Lewis method for 4x4 basically reduces to Roux for a 3x3. Pause. If you already know how to do Roux on a 4x4 up to CMLL, then you can skip to 455, which is where Weird Lewis deviates from typical methods. So if you're a Roux solver, you know that starts with first block, which means solving this 2x1x3 block in the lower left. For most solvers, the colors of the two blocks are any opposite colors that aren't white or yellow. So on 4x4, for Weird Lewis, we're going to choose the first two opposite centers to be any two opposites that aren't white or yellow. Here, green is looking pretty good because we have 3 and 1, so we just go like that. This is probably very familiar to Yao solvers. So here's blue, which should be opposite green, so I'll go like this, and then put it on the top like that. So that preserved our green, we have our blue, and now where's the other blue bar? Well, it could be these guys. So a few moves like that, and now we want to set them to be on top of each other like this to push it up, move it over to the other side, and bring the other bar back down. Next, we're going to pair up any edge that could be our DL edge. Basically, what's going to be right here on the 3x3. So here, I see that for the blue-white pair, it's already one move away from being solved like this, and then it can connect it like that. And I guess I'll just rotate. That completes the down left edge. So the next step is to create two 1x1x3 triplets that are going to go to the sides of that to complete the left block. The first thing I see are these blue-orange pieces because these two are already solved relative to each other. The other piece is right here. There's blue and orange. So I'll bring it to the back like this. Then with a B move, these can be set up with just this wide L slicey thing. And now we have our first triplet, which will go in the back here like this. 1, 2, then B2, 3. 3 moves to create our first triplet. Now where's the blue-red triplet? Well, it's this corner, this wing, and this wing. What I usually try to do in weirder cases like this is put both wings on the M layer, and then if they're both oriented the same way, so the same color is showing, then that's bad, so I'll use like a U2 to set them opposite, and then they can be paired like that on the bottom. And then I guess I'll just go like this and this and this to pair them up, and then bring them down, and then connect it, finishing off our first block. So now it's time to move on to the second block. On 3x3 for Roux, when you're done with the first block, you want to solve the DR edge first, this guy, and it has to have the same down color as the first block. So this one is blue and white, so let's do green and white. It's here and here, so we set them opposite from each other like this. We can pair them up like this, and then connect it like that. So now the DR edge is solved. Now let's look for the two triplets that'll go on either side. Green-orange and green-red are both options. So I see these two green-red edges here, so maybe I can pair them up like 1, 2, 3, like with some weird slice moves. And then this is a pretty good F2L case, but in Roux we can solve it with an M slice, and then pairing that up, we do this to make the pair complete, and then we connect it with all the rest to create the second square. Now I want to create the green and orange triplet over here, and the relevant pieces are this corner, this wing, and this wing. So let's start by connecting the wings, because they can both be on the M layer again. They're opposite, so a single slice move will pair them up right here, and then this is a pretty simple F2L solution as well. There we go, first two blocks are solved. That's pretty straightforward. Now we do CMLL. This step is exactly the same as Roux CMLL for a 3x3, so whatever you get here, you just do the alg. In this case, I got lucky because corners are already oriented and I just have an adjacent swap, so I'll do a J-perm. But you could end up with any of the 42 cases. And now corners are solved relative to each other. All these steps so far are identical to the Lewis method, so they should feel pretty familiar to most speed solvers. This is where the method diverges and gets a little weird. We're going to ignore centers for now and only focus on the 12 remaining wings. The next step is to pair up any two pairs of wings and put them in the bottom layer oriented, which means that either yellow or white has to be on the bottom or top. They do not have to be the wings that will eventually be at the bottom. So in this case, I can see that there's this white and orange wing sitting right here, and its partner is this white and orange wing. So I'll pair them up by going like this and then doing this 3-move insert. You can see that right now the moves that are allowed are U and then like little l, little r, and that's basically it. You can also do like a big M or whatever. So now this set of wings is in the bottom layer. On the other side, there's this yellow and orange wing that's at the bottom that's oriented, so it's good, and its partner is right here. So we'll do a similar thing of putting it to the side and doing a 3-move insert with little l moves, like this. And now both pairs of wings on the bottom are oriented. So maybe it only takes 5 to 7 moves to do this. Now there's only 4 remaining pairs of wings that could be unsolved, so we're going to do a simplified version of wing tracing to figure out if we have even or odd parity. This step is by far the most unique to Weird Lewis, and it's going to feel very mentally intensive, but there are weird tricks you can do to make it take about a second. So let's get into it. Parity can either be even or odd. To calculate Weird Lewis parity, we're going to combine base parity with extra parities, and you need to know how to do both. Let's go over how to determine base parity. Look at the wings and see where they want to go to pair up. So in the back here, we have this yellow-green edge that wants to go here, and the yellow-red edge wants to go here, so we have this sort of 2 swap. And then in the front left, we have the white-red edge wanting to go here, and the yellow-blue edge wanting to go here, so these also want to do a 2 swap. So we kind of have a Z-perm-like shape here, and that means we have even parity, partly because a Z-perm is possible on a 3x3, so the base parity for this case is even. When you're starting off, it's helpful to just say aloud even when you're done with this step. Now let me show you another case. So here's another 4x4. We have yellow-orange wanting to go here, white-blue wanting to go here, white-orange wanting to go here, and white-red wanting to go back here. So this completes like one giant 4 cycle. So this 4 cycle has odd base parity, also because it's like an O-perm on a 4x4. You can't get this on a 3x3. It's a parity PLL. Some other cases you might get are like this, where you have 2 paired edges. Notice that orientation doesn't matter right now. And then you have these 2 edges that want to swap. This is a lot like this PLL, the adjacent swap. And this is a parity PLL, so we have odd base parity here. Or you might see you have exactly 1 paired edge, which means these 3 form a sort of U-perm, a 3 cycle, which means you have even base parity. That is how you figure out base parity. Now let's move on to the extra parities. For this step, we're going to look at each pair of wings on top individually. There's 3 possible cases. Either both are oriented, meaning yellow or white is on top, both are unoriented, meaning not yellow and white are on top, or we have one of each, like this. And I'll call this a differently oriented wing pair. So remember how you shouted out even when we finished base parity? Well, now we're going to go through these 4 pairs, and if they're both oriented, we do nothing. If they're both unoriented, we flip the parity. So now we're going to shout odd. Here's an oriented pair, so we do nothing. And here's an unoriented pair. So we're going to flip the parity again, and we're back at even. That finishes off the extra parities, meaning this whole case has even Weird Lewis parity. That's pretty straightforward, but what do you do in these cases, where you have differently oriented wing pairs, DOWPs? Well, in all cases of the method, you'll either end up with 0 DOWPs, 2 of them, 1, 2, or 4 of them, 1, 2, 3, 4. Let's take a look at this case study. So for base parity, these 2 want to swap, and these 2 want to swap. So it's like an H-perm. So we start with even. Now time for the extra parities. This pair is oriented, so do nothing. This pair is unoriented, so we're going to flip it to odd. Now it's time to handle the DOWP itself. Because DOWPs always come in pairs, just pick 2 and look at them simultaneously. Between the pair of DOWPs, you'll usually be able to find 2 pieces that look similar, like red-yellow and red-yellow. If they have different orientations like this, where you have good and bad, I'm going to call these fraternal twins because they don't look alike. On the other hand, if you have white-red and white-red, I'm going to call these identical twins because they look so similar. They have the same orientation. So if you find a pair of DOWPs and between them you have any set of fraternal twins, then you do nothing. So we're done here. The weird Lewis parity of this case is odd. But now let's look at this case study. For base parity, green-yellow goes here, white-red goes here, white-blue goes here, and yellow-blue goes here. So it's a big W perm or something, which is odd. For extra parities, well, everything is DOWPs, so I'm gonna start by looking at any two DOWPs. If I pick these two, they don't share any in common, so that's actually the worst case. So instead, I'll look at these two. This yellow-green is oriented the same way as this yellow-green, so these are identical twins. When you have identical twins, you flip the parity, so we go from odd to even. Now let's handle the other pair. I see blue-white and blue-white, but these have different orientations. So these are fraternal twins, and we don't change the parity. So overall, this entire case has even weird Lewis parity. And this brings us to the last and by far worst case you could get. Sometimes you have just two DOWPs like here, and between them there are no shared pieces. Pause, this case is rare, happening less than 10% of the time, so if you don't want to learn it, skip to 1212. So you can't figure out if you have fraternal or identical twins. What you have to do is look at the 4 relevant pieces and pick any 2 that have the same orientation. So either these 2 because they're both good, or these 2 because they're both bad. Now look at those 2 pieces and find their remote twins, so twins that are like farther away. We have white-green and white-blue, their remote twins are over here. And here's the rule. If the remote twins are in the same edge, you flip the parity. If they're in different edges, you don't flip the parity. So in this case, the good edges are white-green, white-blue. Here's white-green, white-blue, they're in the same edge. The base parity was odd, so we're going to flip the parity back to even. But look at this different case. We still have a 4 cycle for base parity, so odd, and we also have 2 differently oriented wing pairs. So if we look at the oriented pieces, white-green, white-blue, and look at their remote twins, well here's white-blue and white-green. They are in a different edge, so we don't flip parity. We keep it with odd. That's pretty difficult to do quickly, so rest assured that this case is rare. Also, feel free to screenshot this image, which describes all the rules for calculating weird Lewis parity. But back to our original 4x4 solve. We calculated that the parity was even, but what do we do with that information? Well, now we're going to ignore the wings and focus only on the centers. We're going to solve all 4 of them. The moves that are allowed in this step are the same. We can do U moves, little L moves, little R moves, and M moves. So we use the fact that our parity was even to solve our third center using an even number of slice moves. A slice move is any move that breaks along this center line. So this is a slice move, this is a slice move, but this is not a slice move. So looking around the cube, the easiest center to go for is definitely orange because we have 3 here, and here's the 4th one. This is very easy to solve with 2 slice moves. 1, 2. And there we go. With the third center solved, parity is locked in place. You can now safely forget if it was odd or even as you continue the rest of your solve. And now we just do the rest of them, this guy, and this guy, however we want, as long as we don't really tamper with the orange one too much. So I'm gonna bring our orange center to the bottom using an M move, and because orange is here, the white center should go here. So here's one piece, there's another piece, do a U2 and then grab it like that. And fortunately, none of these moves will disturb the corners. The other white pieces are here, so I'm going to do an M move to put it on top, put it on the opposite side from that one, and then do 2 moves like this, bring it to the other side, and then undo those 2 moves, and then push it all back up. White is now solved. Red should go in front now because the white is on the bottom. So we have 2 red bars. I can do U2, little r, U2, little r prime, and that solves all the centers. Rewinding back a bit, what if we get this case? So we have a 2 swap, base parity is odd, and then we have unoriented, so it's even, odd, odd. So overall, everything is odd. We have to solve our third center using an odd number of slice moves. So what do we do here for green? You might instinctively want to go 1, 2, but you're not allowed to do that because 2 is not odd. What you should instead do is 1, and then push it to the side, add an extraneous slice move like this, which is 2, and then bring it over and then do 3. Now you've got the green center solved with 3 slice moves, and you should be able to finish the rest of it without parity. Back to the original solve after centers are done. For the next step, we want to pair up the 6 remaining edges, but because the centers are all solved, we can only use commutators, but that's not too bad since commutators are 8 moves. For each commutator, we want to pair up 2 edges at once unless we have to cycle break, but I'll explain that when we get there. In this instance, I see the white-orange edge and its pair here. I want to line them up so they're on opposite sides of the middle line. So I can do that with an M move and a U move, which put them on the opposite sides like this. Now, how are we going to pair up 2 edges at once? Well, I'm allowed to make as many M moves as I like without disturbing this white-orange duo, so I'm going to bring it right here, because if I pair them up like this with a little L move, the guy that's kicked out is this yellow-orange edge. So what I want to do is find the other yellow-orange edge, it's right here, and the goal is just to make it so they look symmetrical along diagonal lines. So if I have it like this is not symmetrical in any way, and they're also fraternal, I guess that's a way of thinking it, but in this way, they're identical and they're symmetrical. So this is good because when I push the yellow-red wing out of the way to create the white-orange pair, then I can do just R and U moves to replace this guy with this guy like this. It's always a 4 mover. And then when I undo that first move, these guys will be paired up and then I undo the 4 mover. So that's the commutator form, A, B, A prime, B prime. And now the white-orange pair is paired up and the yellow-red pair is paired up. The next pair I see is this yellow-green pair. This guy's twin is over here, so they are on opposite sides of the middle line, being able to be paired up like that. But let's not do that quite yet. We want to do 2 at once. Yellow-blue is right here, so that's the easiest one to go for. So you might expect us to just go like this, which creates this symmetry because then we can solve 2 at once. But there's a caveat. When you have a 4 cycle of edges around the cube, meaning 2 are solved, you actually only want to pair up 1 edge, not 2. Future carry here. Don't worry about this caveat because it only saves you like 2 moves. It's okay if you always try to pair 2 edges at once. So in order to prevent this yellow-blue pair from pairing up, I'm actually going to make it asymmetrical. See, there's non-symmetry, and then focus on the yellow-green pairing. Always when we pair it up, we kick out the other one like this. Replace this pair with this one, 1, 2, 3, 4. Undo the first move, and undo the 4 mover, 1, 2, 3, 4. Now, why did we not pair up the yellow-blue edge? Well, if we did, we'd be left with 2 unpaired edges, but now we're left with 3, which is actually the easiest case to solve. So for 3, let's bring those up to the top with an M move, and then yellow-orange is looking like the easiest to pair like that. But let's not do that yet. We do want to pair up 2 edges at once because the third one will be paired up by process of elimination. So we do want a symmetry here with yellow-blue. And now let's pair up the yellow-orange like this. Replace the paired up edge with the new one like this. Undo the first move and then undo the 4 mover. And there we go. The yellow-blue is paired up, the yellow-orange is paired up, and all the other edges are paired up as well. This stage should be looking familiar because it's just LSE for Roux on 3x3. And if you did your parity calculations from earlier correctly, you should be able to count an even number of unoriented edges. Here it's just 2. If you did it incorrectly, you'll end up with an odd number and then you'll have to do OLL parity, which is not fun. But theoretically, that should never happen. So in this case, you just do LSE, which I'm not going to make a tutorial for because there's a lot of them out there. But this LSE will never have OLL parity, but you might still end up with PLL parity like this. Or actually, I guess I'll go like this or something. Yeah, PLL parity. But the algs for fixing PLL parity are much shorter, so you don't really have to worry about that taking up too much time. And there you go, the cube is solved. There is a 50% chance you end up with just PLL parity, and a 50% chance that you have no parity whatsoever. And it's always so satisfying. Let's rewind to the final edge pairing stage and go over a few other cases you might run into. What if you're at final 6 edge pairing and you end up with a case like this? You're supposed to pair up 2 edges per commutator, so you can see that white-green here can be paired up like this, and you're like, well, I should pair up a second edge as well. Here's white-blue, but then here's also white-blue, so you can't really move any of them out of the way. Well, then you just cycle break, which is what I mentioned earlier. Just take any other unsolved edge and pretend that's just the one that should be inserted to replace the solved edge. So when you pair it up like this, bring in these 2 random pieces, who cares where they're going to go, undo the move, and then undo the 4 mover. This will pair up just that one edge, and none of the rest will be solved, but that's okay. Okay, but what if you're wrapping up edge pairing and you end up with a case like this? You have just two unpaired edges and the rest are all paired up. You have two possible options. The first option is to unpair a random other edge, which will give you a 3-cycle which you can solve. The way you do that is by setting up your two unpaired edges in the opposite way you'd expect. So if you were to do a slice move here, there's white, blue, and white, blue. Nothing will get solved if you do that slice move, but you want that because we're going to rope this random edge into the mix when we pair it up. So there it is. Replace it with yellow-blue using only R and U moves. Undo the slice move. Undo the form mover. And now we have 1, 2, 3 unpaired edges, which can be solved with a normal commutator. So we have yellow-blue, yellow-blue. Here's white-blue, but that's not symmetrical. So now with an M move, these guys are symmetrical. Pair it up. Replace with that third one. Undo the slice move, undo the form mover, and now we're at LSE with an even number of bad edges, which is good. What's the other option? Well, it's to do some setup moves to a more advanced commutator, which is actually more move efficient. So in this instance, these are the last two edges that need to pair, and we can solve this by sending this guy, the white-blue, to here, the other white-blue to here, and that'll send the white-red back to here, finishing off the white-red pair. Now, how can we do a commutator from here to here to here? Well, if we do a 2-move setup, LYD prime, now it's from here to here to here, which we can solve with a pure 8-mover. 3-move insertion like this, U2 interchange, undo the insertion, undo the interchange, and then undo the setup moves. And there we go. All edges are now paired and we're into LSE. If you have the other case where the last two unpaired edges are like this, white, blue, and white, blue being opposite, you just do the inverse of that alg. So same setup moves like this, but start off with the interchange, the U2, and then insert, and then undo the interchange, and then undo the insertion, and then undo the setup moves. And now you're at LSE again. Oh, you might think, that 2-swap alg is nasty. The whole point of Weird Lewis was to not require a parity algorithm, right? But didn't you just replace a 15-move one with a 12-move one? Lame. That's true, but 1, I can logically understand how this alg works. It's a 3-wing cycle, whereas traditional OLL parity algs feel completely random to me. Comms are typically more finger trick friendly too, because every move does its inverse later on. And 2, you can technically always avoid 2 swaps by choosing smart 3 cycles, like the caveat for the 4 cycle I mentioned earlier. I drew this flowchart, which shows that most cases can be solved with 2 3 cycles or fewer, and 98% of cases, basically all of them, can be solved with 3 3 cycles or fewer. No parity alg needed. Also, the number of squares in this diagram tells you how likely that case is to show up in a real-life solve. Speaking of real-life solves, here's me doing one. You'll be able to see what this method is like at a faster speed. So, time for the conclusion. Do I think Weird Lewis is a viable method for speed solving? Absolutely not. You might have realized it takes 2 to 3 seconds just to calculate parity, so couldn't we just do the standard OLL parity alg in less time than that? Indeed, you could, and if you're going for speed, you should. Also, speed solving the last 4 centers with only slice moves is so awkward. So by contrast, the reason someone would learn this method is as a fun curiosity, not to break their PRs. By the way, in the video, I'm about to start tracing parity, so take a listen. Odd, even, odd. That was fun. Anyway, say you're fidgeting with your 4x4 out in public, so you want to try a method that's quieter and takes fewer moves. Then Weird Lewis might be a good fit. I find it so satisfying to finish the edge pairing stage and see that my LSE has no OLL parity. It means I did my tracing correctly. I do mess it up maybe 5% of the time, but that's pretty rare. I also think that with practice, determining Weird Lewis parity could take under a second as long as there's no DOWPs. Those are the hard to read ones. You can actually remove DOWPs with a quick sub-1 commutator, but in the interest of keeping Weird Lewis a low move count method, I didn't explore that further. Finally, I couldn't finish this video without mentioning Ari Rander's person. I felt inspired to experiment with this method in the first place after I watched his videos on OPA, so this video definitely wouldn't have happened without Ari's work first. In fact, the whole process of solving first 2 blocks and then the bottom before tracing parity was just my attempt at making ARP tracing a bit shorter and easier for me to figure out. Anyway, thank you for watching my speed cubing videos, and I'll see you later. Bye!